It's about 9:01, I think, or thereabouts. So we'll go ahead and get started. We have a really special opportunity today to listen to Dr. Majdalani. We all become quite familiar with our faculty colleagues and sometimes don't realize the importance of some of their contributions. Dr. Majdalani grew up in Lebanon, got a graduate degree in the University of Utah, and then went to Marquette. And over the period since he went to Marquette, he's published about 325 papers, journal articles. He has been cited about 19,000 times, including several thousand citations for the book that he co-authored. Mr. Sleuth was one of the greats in our field, Frank White. And so also over those years, he's been given the Abe Zarm Award 3 times. I think only one other person may have won it twice, and most, very few people ever win it more than once, and it's a rare occurrence even to win it once. And just to kind of put that in perspective, it's an award that's not applied for. So I couldn't nominate Dr. Majdalani for that award, or nobody else could. It's an award that's selected based on student papers, student presentations, and student performance. And it's given to the student mentor. So very high honor just to get it once. And Dr. Majdalani has had 3 students to share that award with. He also won the Lee Atwood Award, which is another almost impossible to get award for all the excellent work that he's done throughout his career. We've talked a long time, but this year I nominated Dr. Majdalani for the Kármán Lecture. And the Kármán Lecture ordinarily is given at the Aviation Conference in the summer, or has been. This year is given at the Ascend Conference just about a month ago in Las Vegas. And so Dr. Majdalani gave that lecture, and as you might be familiar, we're now recording some of the more marquee lectures for our department and put them on the department webpage. And so my suggestion was that Dr. Majdalani come and give his Kármán Lecture as part of that series. And so turn it over to Dr. Majdalani.
Thank you, Dr. Hartfield, for this very nice introduction. I'm absolutely thrilled to be here to talk about one of my personal heroes, Theodore von Kármán. So if you are in aerodynamics, you're in for a treat. If you're not in aerodynamics, we're going to try to keep it entertaining. So today we're celebrating the centennial of the von Kármán momentum integral approach. That's the most significant contribution by Theodore von Kármán. We're going to talk a bit about the history leading up to it. We're also going to talk about its applications and how it's still very relevant in today's world. Okay, so let's talk about von Kármán, the man himself. Most of you know him as the father of aeronautics and astronautics. He is a true prodigy, a true luminary. If we look at his accomplishments, there are quite a few. We're going to go over some of those today. I'm sure you've known some of them. We're going to look at some of the additional contributions that you may not be familiar with. But the story really starts in 1926 when Dr. Robert Millikan, who was a Nobel Prize laureate at Caltech University, sought him out, went to Germany to try to invite him to move to the US. Von Kármán accepted, and in 1930, he became the director of the Guggenheim Aeronautical Lab, GALCIT, and after that, his contributions started pouring in. In 1932, he established the U.S. Institute for Aeronautical Sciences, which later would become one of the 2 arms of AIAA. Most of you are AIAA members, but perhaps you do not know that von Kármán was actually the father of AIAA. AIAA later was formed as a merger of this institute and the American Rocket Society. Shortly thereafter, he established the Jet Propulsion Lab, one of the most well-known research labs in the world today, and also Aerojet, currently Aerojet Rocketdyne. Moving on, he was instrumental in establishing several advisory boards that are still active today. One of the most famous ones is the Science Advisory Board for the Air Force, and also NATO's AGAR. That's the advisory group for aeronautical research and development, AGAR. And moving on, he established an institute in fluid dynamics, later named after him, the von Kármán Institute. I know one of my students went and spent the summer there this past summer, and also established the International Council for Aeronautical Sciences and the International Academy for Astronautics. So he's had numerous contributions in establishing new entities that help promote aerospace engineering worldwide. But what is also not so well known about him is that he had two careers, really. He had two careers. So most of us know about his career in the US. He became a US citizen in 1936. But before that, he was in Hungary. He was born in Budapest, Hungary. We have to give special credit to his father because he discovered his prodigious mind in mathematics. There are stories that even when he was 6 years old, he could multiply faster than other adults could read. Adults with paper and pencil could not calculate as quickly as von Kármán could calculate mentally. And recognizing his mathematical skills, he encouraged him to move on at the time to one of the most prominent areas, to Göttingen, where Ludwig Prandtl had his famous Aerodynamics Institute. So after receiving his bachelor's in mechanical engineering from the Royal Joseph Polytechnic University, this is a university named after Emperor Joseph II, okay? And he got his bachelor's degree with high honors. He worked for a short stint as a professor in hydrodynamics in Hungary, and later on received a 2-year fellowship. Guys, 2 years. He went to Göttingen, and within these 2 years, he was able to receive his doctorate working with the famous Ludwig Prandtl. We're going to talk about Professor Prandtl in just a little bit. But after that, of course, he taught at Göttingen as an instructor. And later on, applying to different jobs, he was able to find a place in Aachen where he went and single-handedly established an institute for aerodynamics, later the Aachen Aerodynamics Institute, that later on becomes famous worldwide. So now, in terms of accolades, von Kármán perhaps is very unique. He's perhaps one of the most illustrious names in aeronautics. If we try to look at the awards that he has received, there are quite a few. If we try to look at some of the most famous, the Wright Brothers Memorial Trophy, the Medal of Freedom, the Gara Memorial Award, every single one of those is really a lifetime achievement medal. And the two most interesting to me were the Air Force Association Science Trophy. That's a very big deal. Later on, it was renamed after him as the von Kármán Science Trophy, and the National Medal of Science. This was a medal. This is one of the most prestigious medals anyone could receive in the United States, and it was conferred upon him by JFK himself. And what is interesting is both JFK and General Hap Arnold from the Air Force, who gave him the Science Trophy, said almost the same things about him, that he embodied truly education, science, and engineering. We could not think of a person who could embody those three aspects more closely than Theodor von Kármán. So after that, we look at some of the other medals that he has received. So we have quite a few medals. The Guggenheim Medal, that's a gold medal. The Franklin Medal after Benjamin Franklin. The Lord Kelvin, Christopher Columbus Medal, the James Watt, the Royal Aeronautical Society Medal. Each one of these medals is really by itself a substantial award that one could receive, and highly competitive. And for him to receive all of those really speaks volumes about the contributions that he's made to advancing aeronautics and astronautics. And in addition to those, of course, we look at foreign awards. He's received lots of accolades from France, Germany, Spain, Italy, and so on. some of the most distinguished. And he's received 29 PhDs, honorary PhDs from 29 different universities. I don't know if you knew that. It's really difficult to get one honorary PhD. I think President Bill Clinton received one honorary PhD from perhaps his alma mater, and he received 29 of those. I don't know if anyone else has received as many. Most of us will be happy to get one PhD in a lifetime, right? Like you're working on it right now. So also, besides those, he was inducted as a member of the National Academy of Sciences, the Royal Society. That's a really big deal to become a fellow of the Royal Society. And it's even more difficult to become a foreign fellow of the Royal Society. And he also was on more than 24 other academies in 9 different nations. One thing about Theodor von Kármán that is not talked about a lot, that his charisma. He was very charismatic. Everybody loved him, and wherever he went, and really it facilitated his ability to get things done, okay, to move things forward. And so also another thing that's really significant to think about is that there are 4 national labs that are named after him worldwide. And of course, the von Kármán Institute has a lab named after him. Caltech has a lab named after him. His alma mater in Budapest, the Royal Joseph Polytechnic, changed its name over time. It's the University of Technology and Economics now in Budapest. It also has a lab. The Theodor von Kármán Wind Tunnel Lab, and of course, AEDC, if you've been to Arnold's Engineering Development Center or Complex, I spent 10 years adjacent to that facility. I visited personally that lab. I think Cody visited the other lab at VKI, right, Cody? So we've visited a couple of those. And what is unique about the Tennessee lab is really the witness of von Kármán. Upon receiving that recognition, General Arnold was going through the inauguration ceremony. He said, "This must be the greatest honor of my career," because typically we wait a few more years until I've passed away before we name a lab after me. But since you insisted on naming it while I'm still around, it must be the greatest honor of my career. I thought that was really nice of him to say that. And so moving on, when we look at the person, besides the contribution, again, the reason I wanted to go through these awards, you would not win these awards if you had not done something to deserve them, right? Typically, you'd have accomplished something significant. But perhaps his most enduring legacy, if we look at his most enduring contributions to the world, could be found in the people that he touched, the people that he mentored, the people that he worked with. And if we look at some of his advisees, we're looking at some of the biggest names in the community. I'm going to start backwards. Okay, if you look, his first PhD student was Maurice Biot. There's the Biot number named after him. I'm sure most of you have studied the Biot number if you've taken heat transfer. Otherwise, you've heard of the Biot number. But you go around that list, and this is, by the way, a very partial list. We just tried to pick on some names that are important to us. There is William Sears, who was instrumental in advancing Northrop Grumman, and then became a well-known professor at Cornell University. We have Martin Summerfield, the Martin Summerfield Award, who went to Princeton. He had at least 50 doctoral students who later became professors all over the world. There is Frank Marble, who also stayed at Caltech and had over 50 PhD students. So we look at a true legacy that he left behind, and it is those workers that are still advancing aerodynamics and astronautics in the world today. But also, von Kármán really grew up in very good company, we could say. According to John Anderson, most of you know the well-known author John D. Anderson, the greatest aerodynamic group in the world at that time was in Germany. It was the Ludwig Prandtl group. And I'm going to go over some of the colleagues that von Kármán had. Truly astounding. These are names that you've studied. There are methods. If you've taken gas dynamics or Aero 2, you would have come across some of those names. And We start with Blasius. Okay, Blasius happened to be the inaugural PhD student of Ludwig Prandtl. So when he started his institute in Göttingen, his first student was Heinrich Blasius, who turned out to be a true prodigy. Later on, becoming a professor at the University of Hanover and also leaving behind his own legacy. Most of you have taken aerodynamics or Aero 3, have heard of the Blasius equation, right? Still used as a benchmark for new computational methods being nonlinear and difficult to solve except by computer, numerically. Von Kármán, 1907 was Blasius, 1908 was von Kármán, then Theodor Meyer. So we had Theodor von Kármán, then followed by Theodor Meyer, Hemans, Polhausen, Nikarutse, Busemann, Glauert, Eckert, etc., and many others. If you have, again, studied gas dynamics, you probably are familiar with the Prandtl-Glauert expansion, Prandtl-Meyer expansion, and so on. So there are numerous formulations that were developed by some of these amazing scholars. We're going to talk today a bit about Blasius, of course, and Polhausen, and perhaps Hemans a tiny bit. The institute at the time was known as the Kaiser Wilhelm, Kaiser like a King Wilhelm. Today it's known as the Max Planck Institute, very well known and authority. If you're the director of the Max Planck Institute, you're sitting in the Prandtl chair today. So it's a highly sought after position. There are some faculty from Stanford who apply to it and move around. It's considered to be one of the most prestigious positions in the field today. And also, it's important to look at the lineage. I always love to look at the lineage when we're studying the history of an individual. So we can see here that von Kármán was a student of Ludwig Prandtl. Everyone knows that. But also, Prandtl was a student of Professor Vöpel, very well known all over the world. Vöpel was a student of Felix Klein. Now, the entire Göttingen University was at the time the mecca for applied mathematics, and that was thanks to Felix Klein. Felix Klein was an eminent scholar in applied mathematics, and many sought that school because of the rigor that it instilled in everything that it offered. And Klein was a student of Lipschitz Dirichlet, a big name in mathematics. If you try to get a degree in applied mathematics, it's a very big name. And of course, Joseph Fourier and Joseph Louis Lagrange, two of the biggest names in mathematics, who again lead us all the way back to Leonhard Euler, the greatest mathematician to have ever lived. So really amazing legacy when you look at von Kármán and how he is connected all the way to Euler. Euler is, many call him mathematics incarnate. Okay, incarnate. He really added more to our understanding of mathematics than anyone else. Most of the symbols that we use in mathematics today are thanks to him. He unified all the symbols that are used worldwide today. And when Theodor von Kármán passed away on May 7th, 1963, sadly, it was also the same year JFK was assassinated. So JFK gave him the National Medal of Science, I get the chills, gave him the Medal of Science, got assassinated that same year, and the same year, in 1963, Theodor von Kármán passed away, and poetically, he passed away in Aachen. He was visiting Europe, promoting AGARD, NATO, and went back to his hometown where his first career started, where he became world famous in Aachen, and that's where he had a heart attack on May 3rd, and on May 7th, 1963, he passed away. So when he passed away, one of the most prestigious societies in applied mathematics in the world, the Siam Society on Applied Mathematics, invited one of his most celebrated doctoral graduates, Dr. Sears, Bill Sears. You should know that name, numerous contributions in the field, who was a professor at Cornell University, was department head. He established the Aero program at Cornell, and later on, when he stepped down, he went and became director of the applied math department. So he was directing two different departments at Cornell. He was invited to write his in memoriam. Now, instead of writing an in memoriam that talks just about his biography, he decided to give the world insight into his life and who he truly was. He published a technical note, I encourage you all to read it. This being a lecture, an invited lecture, I would encourage you all to look up this paper in SIAM Journal of Applied Mathematics. It's titled Some Recollections of Theodor von Kármán. I've read it at least 7 times. It is amazing, and everyone who's read it, my students have read it, will tell you they found it to be very enjoyable, right, Daniel? Very enjoyable paper, and so do grab it if you can. You will not regret it, okay? It's very short, by the way, and there are no equations in it. So now, and in it, we're gonna cite some of the things he said. One of the things he said, it was clear to those of us who worked close to him that mathematics, applied mathematics, was his true love. Although he was a leader of leaders in aeronautics and astronautics, established more institutions and committees and advisory boards than anyone else, but his true love was found in applied mathematics. Now, I mentioned earlier, von Kármán is my personal hero. You may wonder why. So, Professor Sears at Cornell taught a gentleman by the name of William or Bill Van Morum. Professor Van Morum later on went to the University of Utah and taught. I happened to be his doctoral graduate, and Professor Van Morum used the notes. He used to tell us some of these stories I'm sharing with you, but he used the notes that von Kármán passed on to him through Dr. Bill Sears. So Dr. von Kármán to Dr. Bill Sears to Dr. Van Morum and to me. And I've been using those notes for the last 30 years to teach aerodynamics and aeroacoustics and perturbations. If you've taken those courses with me, you probably have seen there's a lot of von Kármán in them and very well organized, and they tend to really start from the specific and go to the general, which was very important for von Kármán in teaching. And by the way, he was an exceptional teacher, something that we sometimes overlook. And let's talk a bit about what von Kármán was famous for, the von Kármán vortex treat. This is for flow past a cylinder. It's a problem that actually Ludwig Prandtl was trying to crack to solve with his student Hemans, okay? And it was an experimental project in a laboratory, and they noticed that no matter what they tried, the flow would not remain steady. And Hemans would go back to Prandtl saying, hey, it keeps oscillating no matter what I do. It's your fault. Go back and redesign it. Try to make it more symmetrical and try again. The flow should be totally symmetrical over a cylinder. And that, of course, baffled Dr. Hemans until one day von Kármán mathematically went through the stability equations and were able to demonstrate that this flow is unstable. It leads to oscillating, alternating lateral forces on the cylinder, and he made the discovery while he was in the tramway, wrote it on the wall of one of those wagons, and he had to go teach, so he left that station, and then later on forgot how he did it, so he sent all of his students and colleagues looking for every single wagon to find that solution that, of course, later on became quite famous. It's taught now in most textbooks on the subject. So the other thing he's known for is, of course, the Kármán constant, the universal turbulence constant, kappa equals 0.4 in conjunction with Prandtl's mixing length theory. You see that when you try to model the log of the wall, the overlap or inertial layer, as we call it, we come across that constant. Another contribution that's named after him is his analysis and prediction of the edge of space, or in other words, the Kármán line, where outer space or free space where there are no jurisdictions begin. The atmosphere is kind of enclosed within that region. It's about 100 kilometers. And the other one you probably may or may not have seen is the friction factor equation named after von Kármán for smooth pipes in conjunction with the Moody diagram that is used to solve pipe flow problems. But if we go and do a literature search on the Web of Science, we find that by far his most widely cited paper is his paper in which he introduces the momentum integral approach. So the momentum integral approach is one that, again, has become standard content in most textbooks in fluid mechanics and aerodynamics. It was published in 1921 And incidentally, the physics of fluids had a Centennial issue, a special issue to commemorate that very significant contribution here that I happen to be part of. A lot of good contributions came in, including some from Stanford. Professor Brian Cantwell, who was the former Aero-Astro department head at Stanford, about a new universal velocity profile, and also from Ohio State University on using the Kármán momentum integral equation, and some from our own team. This one is by Rudy Al-Amar, who most of you know. Is Rudy here? All right, so if we look at most textbooks on the subject, again, from Wiley to McGraw-Hill to Pearson to AIAA, it's difficult to find a book in which the momentum integral approach is not presented and taught, and we're going to try to focus on that a bit today. But to put it in context, it's very important to go back to one of the most revolutionary papers, to use the terms used by John Anderson. So back in 1904, Ludwig Prandtl presented what we now refer to as the boundary layer equations. Up to that time, the analysis, fluid mechanical analysis, was limited to the far field using Euler's equations. We could not figure out how to model the near field and how to match the near field to the far field. And in this very short 8-page paper, pretty much Ludwig Prandtl presented the way around that. He showed how we could match the near field to the far field. He had a significant contribution to perturbation theory, what we now call the Prandtl matching principle, leading to a uniformly valid solution that works correctly everywhere in the entire domain, all the way from a surface to the far field. And he also showed us how we can capture the skin friction coefficient, the drag, and many other boundary layer characteristics that were thought were impossible to determine. They all went back to the simplified equation of the Navier-Stokes formulation. Again, at its own Centennial in 2005 in Physics Today, John Anderson published another technical note, another recommended read for you. You can find it online at Auburn. You can download it. It's in the Physics Today. That kind of describes the importance of that scientific contribution by Professor Prandtl really well. And in it, Anderson says, if we could give someone a Nobel Prize, it would be this paper by Prandtl, because it really advanced our knowledge by leaps and bounds. And also he quoted Sidney Goldstein, who wrote about it that it was a revolutionary paper. So a really good paper for you to look at. Now, again, sometimes things happen, the stars are aligned, things happen for a good reason. And 3 years after the introduction of the boundary layer equations, the first PhD student of Professor Prandtl was Blasius, who figured out how to use a very clever transformation to convert those partial differential equations into an ODE that could be solved numerically. Okay, now some have attempted power series solutions and different types of series solutions, but typically it's assigned and solved using Runge-Kutta. Most of you have heard of it. In this equation, Xi is the Xi here is the Blasius similarity transformation, or a variable transformation, and F is the normalized stream function. They go hand in hand, and they allow you to basically start with the boundary layer equations, convert them to a simple two-term, nonlinear third-order ODE that you can solve numerically. I'm sure most of you have heard of the Blasius equation. If you have not, then you need to look it up. Okay. But in 1921, in response to that, now of course the Blasius solution was considered to be exact. It was highly accurate, but it applied only to the problem of flow over a flat plate. It was not very general. So in response to that, in 1921, von Kármán introduced his momentum integral equation that was much broader, much more universal. It was applicable to both turbulent and laminar flows, and it was really instrumental in determining the skin friction coefficient. And it was published as with Karl Polhausen. It was a sequence of 2 papers, 1 and 2. They were sequential in ZAM, the Journal of Applied Mathematics and Mechanics. And in these 2 papers, we had the tools needed to solve a problem comparable to that of Blasius. So if we look at the equation itself, and again, we're not going to spend too much time on it, but in order to find the shear stress or the skin friction coefficient, we needed both to define the normalized velocity within the near field. That's the velocity approximation inside the viscous boundary layer. That's very important to model. To have some kind of approximation for it, we're going to use little u over capital U, which is little f, to denote that normalized velocity, and eta, which is the fraction of the boundary layer thickness. Okay, so eta here is y over delta. And in order to model that near field, we also need the far field, which is typically known. There have been many studies that showed how you could obtain capital U. So if you have capital U and you have little u, you can essentially solve that equation. And the reason we had 2 separate papers, Polhausen, one of von Kármán's colleagues who followed him to Aachen when he became a professor at Aachen, both of them published it in the same issue. Polhausen provided the approximation for the near field that was necessary to use the momentum integral equation. And so in a nutshell, we have the far field, we have the near field. Both of them are substituted back into the momentum equation in order to obtain all of the boundary layer characteristics that you know of, the displacement thickness, momentum thickness, shape factor, skin friction coefficient, etc. Everything can be obtained out of that. And again, according to John Anderson, this was a very important contribution because not only it generalized the way we can use and solve boundary layers, it made it much more applicable to a large variety of problems. It made the boundary layer approach more popular worldwide. Now, let's get to the nitty-gritty, okay? So this is where we're going to look at some of the interesting elements of this approach. Over here on the left, and this is a table taken from Fox and McDonald's Introduction to Fluid Mechanics. It's widely used, one of the most popular books worldwide by Wiley. This is a table that is taken from there. You have KP1, KP2, KP3, KP4. These are the polynomials that refer to the order of that approximation. The velocity approximation is done in the form of a polynomial, and KP1 would be a first order polynomial, 2, 3, and 4. 4 is the highest order polynomial that was introduced by Polhausen. Now, for every particular approximation, one can find beta, which is the normalized momentum thickness. You all know what the momentum thickness is. And a couple of parameters we're going to talk about a bit here today. One is A, one is B. So A is, in essence, the characteristic boundary layer thickness. If you know A, you know exactly how to determine delta, which is the boundary layer thickness. And B will represent the skin friction coefficient. If you know B, you know how to determine the drag force immediately. And for every single one of these candidate profiles, one can find these constants. Now, ultimately, you want to try to approximate for any given case the exact solution. So for a flow over flat plate, the exact solution is given by the Blasius solution. So you try to evaluate those coefficients and compare them to the exact values, so to speak. The problem is, as we went to higher and higher polynomials, instead of those coefficients getting closer to the exact values, they moved away from the exact values. So to be more precise, if we try to evaluate the relative error between these different approximations and their exact values, which you could obtain numerically by solving the Blasius equation for flow over a flat plate, you notice that the error only increases when you go to a higher order polynomial. Now, when I was a student and studying this, it did not make sense to me. And I tried to investigate that. I asked every faculty member in aerodynamics that I knew, that I had access to. I continued to question that, because when you go to a higher order polynomial, in theory, you're satisfying more boundary conditions that try to capture the Blasius behavior or the exact behavior. These were postulated by Paul Hausen. And it made no sense to me that when we go to a higher order polynomial that's able to capture more precise boundary conditions, the error increased. It should decrease, right? I mean, why bother to go to a higher order polynomial if you're making things worse? And the thing that was the most staggering, if you look at the boundary layer capture, what we call the disturbance thickness, the error in using the Paul Hausen fourth order polynomial was 17%. It was so large, it led many to abandon entirely the use of the momentum integral approach and go devise new empirical ad hoc techniques such as the Thwaites or the Walls methods. I'm sure you've heard of the Thwaites. They would not have been encouraged to pursue these other techniques were it not for the fact that the momentum integral with the Paul Hausen by themselves were failing. They're giving you errors in the order of 20%. Now, of course, we can live with 5% error as engineers, but 20% was way too much. Now, again, to find every one of these constants for a given candidate profile, let's say I give you in Aero 3 the third order polynomial, you have to go through a bunch of algebra. And again, over time, for more than 25 years, I'm wondering, and I'm asking everyone I've known from MIT all the way to Stanford, why we have this paradox, this perplexing behavior that the error only gets worse. And while I was doing that problem, preparing an exam in Aero 3, I believe it was 2017, I discovered two expressions that held the key to unravel the whole affair, to really reverse engineer the problem, improve the momentum integral formulation, and also find an exact solution to the Blasius numerical equation, or the equation that could only be solved numerically, rather. And that is A and B. Remember, we talked about A being representative of the boundary layer thickness and B, the skin friction. I discovered that they are directly related to two parameters, F naught prime and beta. Beta, we talked about it earlier, if you remember, it was the normalized momentum thickness. It's a number, okay? It's a value you can calculate by simply taking F, multiplying it by the y minus F, integrating from 0 to 1. It's a very simple thing you can do and program. And the other thing is F naught prime. F naught prime turned out to be really negative the vorticity. It is the slope at the wall. It's you take the function, you differentiate it, you evaluate it at 0 at the wall, you get that. And if you knew those, and they have unique characteristics, by the way, A times B gives you 2F naught prime, B over A gives you beta. I thought this was kind of elegant, but the first thing I wanted to do is demonstrate that to myself, make sure that that works. And using, again, these new correlations, we were able, and knowing what the true values, the exact values of A and B were, we were able to reverse engineer the problem. And reverse engineer the problem by comparing it to the Blasius equation. So here we're looking at the Blasius equation illustrated. So it's a solution on the left. You have the normalized vertical distance, y over delta. The horizontal axis is the normalized velocity. And we are going to compare those to the Kármán-Paul Hausen polynomials that were posited, that were essentially proposed by Paul Hausen and used in conjunction with von Kármán's momentum integral approach. So this is the second order polynomial which satisfies only three boundary conditions. No slip at the wall, y equals 0, you have u equals 0, everyone knows the no slip. At the far field, y equal delta, little u equal capital U, you're kind of merging into the far field. And then the other boundary condition is du by dy equal to 0. That's the shear stress, the shear free zone, right, at the edge of the boundary layer. Now, if we go to the third order polynomial, notice that the discrepancy from the red curve, right, the red curve is the exact value, increases. So now we're satisfying more boundary conditions, which kind of does not make a whole lot of sense. And then when you go to a fourth order polynomial, the error increases even more. So again, here's the third order, here's the fourth order. The error becomes much greater. Okay? Now, fast forwarding a couple of weeks, maybe a month of investigation, zooming in on the reason why this could have happened, we discovered that these five postulates, these are the five boundary conditions that were referred to by Paul Hausen as compatibility conditions. One of them was actually incompatible with the exact solution. So the second order derivative, which is the curvature, was not really 0 at the edge of the boundary layer because of the asymptotic behavior of the solution. It continues to change all the way on to infinity. When we evaluated it, we found that it is of order unity. Therefore, you cannot impose that boundary condition. Otherwise, you are going to overshoot the correct solution. Just relaxing this boundary condition and redoing the problem, we were able to get this very simple fourth order polynomial that carries with it substantially reduced errors. We're talking about 2 orders of magnitude reduction in the relative error by simply replacing the coefficients from this to that. Okay, this was really neat. And the 17% error that we talked about that led to other researchers looking for alternative ways of solving this problem, again, was decreased from 17% to 0.13%. We were happy with that, but we did not stop there. There's a paper on this I encourage you to look at if you're interested. I know some of my colleagues have already looked at that, where we go to the 7th order. I show how you can go all the way to the 7th order. You don't need to stop at the 4th order, and with increasing accuracy, you can reduce this error really to 0. Now, remember, one of the neatest things, we're engineers, we love to play with parameters, and that if you multiply A by B, right, what you get. I'm going to illustrate that from the table from Fox and McDonald. If you take any one of these entries in any one of these rows and identify what's your f naught prime. F naught prime just happens to be the coefficient of eta to the power 1. It's really easy. You do it by inspection. If you differentiate the polynomial, set eta equal to 0, you always pick up the coefficient of eta. Okay? If you identify f naught prime and you multiply a and b, you get exactly 2 times f naught prime. I did that by hand. When I did that, I was really thrilled because I knew I was onto something. And if you also do beta, remember we talked about beta times a equal b or b over a equal beta, you also get the same values. So I was really thrilled. No matter what polynomial you use or what function you use, those correlations are exact, okay, that we discovered. And they really held the key to unravel the whole affair. Because if you know what the answer should be, and you can connect it directly, tie it up to the original expression of your assumed polynomial, you can reverse engineer the problem in 2 seconds. So another visual here. This is before. The Blasius is the red. KP4 is the Kármán-Pohlhausen 4th order polynomial. And this is now. Okay, you just, with a simple improvement, we are able to pretty much match the Blasius solution. Now, you may wonder why we have a discrepancy here at the top, and that could be easily explained. When we try to improve upon the KP, the Kármán-Pohlhausen polynomial formulation, we try to compare apples to apples. And Pohlhausen defines the edge of the boundary layer to be y equal to delta, little u equal capital U, so f equal 1. If you notice here at the corner, f is equal to 1. However, in the Blasius model, the edge of the boundary layer is located at 0.99, little u equal 0.9. That's the strict Prandtl definition of the edge of the boundary layer. If you take that into account, that explains the discrepancy. If we repeat the analysis using Prandtl's strict definition of the edge of the boundary layer, we get a polynomial that you could not discern from the Blasius. Okay, so that was, and all of this is found in this paper here that we publish in the Physics of Fluids. All right, so we did not stop there. Using the Reynolds transport analogy, we went and found the Nusselt number for flow over a flat plate for both a uniformly heated plate, a constant temperature and constant heat flux. We were able to reproduce the Nusselt number with an error of less than 0.5%. Now, using the older approach, the error was greater than 10%. So we really hit it in the bullseye, not only in the viscous boundary layer, but also in the corresponding thermal boundary layer. And we did not stop there. We went and tried to solve the Blasius equation exactly. Now, what I mean by exactly, obtaining a solution that's really simple, a one-term solution, analytical, that has an error that is smaller than the error associated with deriving the Blasius equation itself, okay? And I did that with my postdoc, God bless his soul, Li Jun Xuan, Dr. Li Jun Xuan, who passed away in 2020. So we obtained a really nice solution. It really took us 20 minutes. Once we figured out what the key boundary conditions were, we wrote the exponential form, put the polynomial inside of it, and again applied the same optimizer, which had all the boundary conditions within really 20 minutes. We were able to get that solution, which you cannot tell apart from the Blasius. So we have the Blasius, which is obtained using Rangakata, and we have our solution, which is overlaid on top of it, and you cannot tell them apart. This was really significant, and we tried to hurry up and put it in the 4th edition of Viscous Fluid Flow, which was about to be released a month later. So we worked around the clock to get that done, and we managed to do it. By the way, the 4th edition, this is the first edition of any fluid mechanics book that has not aerospace, fluid mechanics that's taught, that's used in mechanical, civil, etc., that has an aerospace engineering engine on top of it. That's the cyclonic rocket engine internal flow field. So we were really pleased to really showcase that cyclonic flow field. Now, again, applying it to other problems, we looked at the flow over a cylinder. This is Rudy who did this work, and we got really good results in terms of prediction, accuracy, and improvement over the traditional KP4 approach. Rudy was able to get an approximation for, let's say, the separation angle with a 0.2% error, which was really insignificant, better than any other model out there. And also comparing it to the numerical solutions and the experimental solutions, everything worked in a much better way. To kind of change the focus to another world, okay, to the world of CFD, and in this case, flight stream, a code that most of you are very familiar with, and Professor Hartfield and Dr. Huja, who really founded this research in flight and developed this really innovative surface vorticity panel code that produces, that gives us tremendous advantages in modeling aerodynamic structures. This particular code needs a little introduction with this audience, since most of you have seen a lot of coverage of what it can do, but very uniquely, it can model flapping, flutter, and morphing. These are aspects of aerodynamics that are very difficult to capture using the more standard codes, the RANS codes. So it's a code that is very robust, very efficient, can lead to very short run times, and yet enable us to capture aerodynamic characteristics for flight articles in a very convenient way. And it's ideally suited for early stage conceptual design of different aircraft structures. So it's despite, again, flutter and fluid structure interaction being extremely difficult to model using RANS, other codes, commercial codes, this particular code is quite robust. And the reason I wanted to mention it, not to help promote it, of course, all of you are intimately familiar with it and you may have used it already, but the fact that it also leverages the momentum integral approach. So if you look at the code itself, the construct, the far field is a potential flow. It's essentially an viscid irrotational flow, but at the surface, in order to capture the surface, one has to use some empirical models, and it does use some of the most advanced empirical models, including the Standen approach, which is sort of a glorified version of the momentum integral approach that takes into account effects of compressibility and thermal variations across the viscous boundary layer. So a very powerful tool, thanks to, again, its ability to incorporate models such as the Standen model and the Swafford model, etc. And not only is it efficient at modeling external aerodynamics, but also internal aerodynamics, in fact that it's been recently applied to the internal ballistics of a solid rocket motor, leading to an award-winning paper here with Griffin. I don't see Griffin, maybe he's watching on Zoom online. So finally, to kind of wrap up, we've also, inspired by von Kármán's approaches, whose legacy we celebrate here today a bit, von Kármán was very keen on approximations. Remember, his advisor was Prantl, who was one of the greatest asymptotic theory contributors in the world. So one of the things he loved to do best is to simplify governing equations to the extent that you can obtain closed-form analytical solutions to them. That's the thing he loved the most. And we kind of followed his approach here in modeling cyclonic flow fields. I'm sure you've seen lots of presentations on that, but we typically followed his approach of using mesh asymptotic expansions, one of his favorite techniques, and simplified the governing equations from PDEs down to ODEs and applied judicious boundary conditions in order to find exact solutions that could be later augmented by viscous approximations to capture boundary layers near the core and near the wall. This is one of those solutions that became quite popular. We were able to find an exact solution to a wall-bounded cylindrical cyclone in a rocket chamber, here published with Dr. Marty Ciavarini, the current director of propulsion for Sierra Space, working on the Dream Chaser. And we also uncovered several important characteristics, all thanks to these analytical expressions. And also following von Kármán's approach of going from the specific to the general, we uncovered a slew of special solutions, but then we generalized with a formulation that could incorporate arbitrary inlets and outlets in a cyclonic chamber. And with that, a number of really beautiful helical flows of the Beltramian, Tercalian, complex lamellar, etc., that have unique characteristics in terms of vectors, the velocity and the vorticity being parallel or orthogonal, etc. I could really spend the whole week talking about those. And amongst the characteristics that we uncovered, the vortex Reynolds number that controls a cyclonic behavior, the diameter of the forced vortex, the wall boundary layer thickness, the maximum tangential speed, and near the center of rotation or the axis of rotation, the angular speed that becomes constant as you approach the center line. Everything becomes what we call, we turn into a forced vortex at the core of a cyclone. So the flow rotates as a rigid body at a constant angular speed, which we were able to predict analytically. And finally, the swirl intensity that we were able to uncover. And one of the key characteristics of this model is the mantle, which separates the outer vortex from the inner vortex in a cyclonic chamber, in a tornado, in a hurricane. And we were able to predict it also using different models. One was cosine-like with a root of 0.707. One was Bessel-like with a root of 0.63. This is essentially a characteristic. Anytime you talk about a cyclone, a tornado, or a hurricane, there's a mantle. It's a rotating, non-translating layer that separates the outer, what we call updraft, from the downdraft. And locating it is a key characteristic that defines the topology of that cyclone. Okay, so we found two different possible routes, and we looked at the literature. We were pleasantly surprised that at MIT, Joseph L. Smith, who was the department head of mechanical engineering for some 20 years, his specialty was hydrocyclones. He was studying that experimentally. He was not a theoretician, and so he found the two routes, according to his experiments, were about 0.62 and 0.72, whereas ours was 0.71, 0.6. We were really pleased with that. It's lovely when experiments and theory agree. And we continued on again from one geometry to the other. We cracked the conical cyclone. We found an exact solution to that problem, published in JFM and other places. And we also, most recently, looked at the hemispherical geometry because of things I cannot really talk about, but it's a great geometry, it's very efficient, and we don't have time to get into cyclonic flows. I just wanted to illustrate that using von Kármán's systematic approximations and mesh asymptotic expansions, we can obtain elegant solutions to some fundamental complex problems that govern rocket flow fields. And with that, I conclude my talk. So in essence, we covered quite a bit of material. We started off by giving tribute to von Kármán and his legacy. We talked about his momentum integral approach. We showed you how we can overcome that perplexing Paulhausen paradox that over 40 years I could not find any satisfactory answer for. We finally discovered that one of the 5 compatibility conditions that are published in every textbook is actually incompatible with the exact solution to the problem that you must obtain numerically and then really compare apples to apples using the same similarity parameter and so on to be able to correct it. And we not only explained the Polhausen paradox, we were able to overcome it by providing alternative solutions that are not deficient in that manner, that reduce the overall error by 2 orders of magnitude. So as a result, we could say that the momentum integral approach lives on. We can continue to use it in conjunction with these newer formulations because it's still highly accurate. And finally, we showed how we can obtain the characteristics of most cyclonic flows using similar approximations. And on the last slide, I'm showing not von Kármán, but Blasius. Do you know why? Many have worked on finding the Blasius solution by trying to solve the equation directly. The key was in using the momentum integral approach that was introduced by von Kármán, his colleague, to reverse engineer the problem and get a solution that's no different from the Blasius solution. And so the Blasius solution now, you can consider it to be resolved thanks to, again, von Kármán. Okay, so thank you very much.
We're pretty close to the hour, but we'll have time at least for 1 or 2 questions if anybody wants to ask Dr. Majdalani a question. I'll just ask one real quick.
Sure.
And that is, you sort of come to a really nice concluding result, but do you have the new things that you're trying to work on with this genre?
The new thing.
New things that you're working on, yeah.
Yes, so we have quite a few things that we are trying to pursue, and we're looking for good men and women to join us. We've kind of scratched the surface of resolving those similarity solutions. There are quite a few other problems that could be solved using similar techniques that we have introduced. The Falconer scan is one example that is a modification of the Blasius equation. We also have a number of other geometries that we would like to extend our analysis to, a number of canonical problems that are out there that we would like to solve as well by applying these techniques to different geometric shapes and flow configurations. So we're really excited. I think we know how to do this, but we just need some hardworking, good folks to help out, because the technique is very elegant and the approach makes sense, but we need individuals to kind of pursue it further.
Anybody else have a question? We really appreciate you coming. Or go ahead.
Well, it was a very, very good presentation, and I learned so much today compared to what I've been learning about these people in my grad school. So, thank you for that.
You're welcome.
What, in your opinion, took so long for somebody to come up with modification to the momentum integral?
I wondered the same. Okay? I was wondering the same. Why did it take over 100 years to crack the problem? And the answer is simple, because I was a student like yourself sitting on the other side, and I tried to figure this out, and I couldn't. In all textbooks, they use the same eta for the similarity transformation that Blasius used, and for y over delta. They use the same f to mean the normalized velocity and to mean the normalized stream function. And there is no way you can compare the two unless you redefine. You have to deconvolute them and then find the connection between them as well. I used to have slides on those. We found the direct connection between the eta that Kármán used or Polhausen used and the xi that Blasius used, and there's a direct connection between them. That's really important to establish. Otherwise, you are not comparing apples to apples. And the derivatives, the same way. The derivative of the Blasius stream function is little f, which is our normalized velocity. So you have to start, if you want to compare the two problems to essentially figure out why they are not matching, it's really important to get to the bottom of it and use the same parameters to compare them correctly. So yeah, it takes a little bit of dedication and patience, and usually once you solve the Blasius equation numerically, you just forget about it. You're so tired solving it, you don't want to do anything else with it, and it's important to kind of find the corresponding variables that you are using in the other approach and compare them one to one.
Okay. I think we're right at the hour, so we'll stop here, but thanks everybody for coming and listening to Dr. Majdalani's lecture. I truly believe you have heard a historic lecture today. This is the stuff that will go into textbooks. So that's a very special privilege.
Thank you so much.
Yeah.
We appreciate it. Thank you.